Okay, let's get started. Good afternoon. Today we have a very fun guest here. It's Alán Aspuru-Guzik from Harvard University. Let me introduce him a little bit. At 2004, he got his PhD in physical chemistry from Berkeley. And then in 2006, he became assistant professor at Harvard for chemistry and chemical biology. And this turned into a full professorship in 2013. Alán, you saw it maybe in the announcement, has a very accomplished resume with a lot of awards. Maybe just to call out two is the MIT Technology TR35 Award for Young Innovators Under 35. He also has a prestigious DARPA Young Innovator Award. And I think it's probably fair to say that Alán spearheaded or founded the group of, or the field of doing quantum computing for chemistry. And that included actually playing as early as possible with emerging quantum hardware. So he was one of the first users of the D-Wave machine, and he's now eager to try out latest algorithms on the chips that come out of the quantum hardware group in Santa Barbara. The talk he will give today is addressing another area of interest of Alán, that is applying big data approaches, machine learning approaches to molecule discovery and material discovery. So looking very much forward to that talk. Thank you.
So yes, I guess my group has two parts. One has to do with materials discovery, one has to do with quantum computing. I came wearing both hats to talk about quantum computing, but also to really talk to you guys experts on machine learning. So let me just begin by stating that if you think about the challenges of the 21st century, for example, even the challenge of water filtration, you might, or purification, you might think about there might be some materials that actually will allow you to do this cheaper, or the discovery of drugs, or the discovery of a lot of energy generation and storage materials. So if you think about a lot of the challenges of humanity, they eventually touch into a material that we could make cheaper, we could make longer lived, we could make better. So this is kind of one of the motivations of what we do, Let's just begin just by counting, just thinking about how many molecules there are. Well, let's just begin by thinking about how many atoms, just single atoms, are in just the visible space. Does anybody have any idea? Order of magnitude? You can be off by several orders of magnitude. We're at Google, we're about off by 20 orders of magnitude. It's 10 to the 82 atoms in the observable universe. So just counting the number of atoms. But if you remember, atoms are kind of like Lego pieces. You can take an atom and combinatorially put it with another atom and another atom and another atom to make a molecule, right? So if now you think about molecules that are roughly accessible by our synthetic techniques, and now there are people that are making robots, like Marty Burke at Urbana-Champaign. They're making these robots to make molecules combinatorially, right? But if you think about how many molecules can you make, right, it's actually a larger number. Chemical space is actually estimated in the literature with a big error bar between 10 to the 60 and 10 to the 180. Of course, in principle, it's infinite because you can keep building larger and larger and larger polymers of, molecular, exponentially growing molecular complexity. But synthetic accessible molecules that you might make, with reasonable amount of cost, we're talking about maybe this order of magnitude. So the chemical space is immense, and the question of how to search it to find the solutions to those problems is what is interesting to me. So what are the tools that we use to actually go and explore in that space? Well, the first thing that you want to think about is maybe this idea, right? Imagine that I have a huge database of molecules, and then I just look at the molecule and pull it out of the database. I actually use the Google Images database, actually. I just pull a random molecule from Google Images, and here it is, right? And the question that I want to ask you is this molecule good for Ebola, or is it good for solar cells, or is it good for storing energy? That would be actually the best possible kind of project that you could do. You could do like a classification of the entire chemical space, right? And we try to go there eventually. But you can also think of a simpler possible idea, which is you take the same molecule and you ask yourself one question, okay, like how good is this molecule as a solar cell material, okay? So you see it's a slightly different problem because now I just, instead of like trying to find all the possible uses for a molecule, let's just concentrate on one. That's what we like to call in chemistry or in materials the screening problem. I want to screen for a particular property. And the tools that I just revealed here already, quantum mechanics and machine learning, are the two tools that we are going to employ. And I use quantum mechanics here, although I think a lot about what is quantum mechanics in the quantum computing side of my life. Here I use quantum mechanics as a mechanic, okay? So I'm not interested in this meaning of the wave function, okay? This is a poem that was written by Schrödinger about Eric Hückel. Eric Hückel was amazing. He actually used pencil and paper during the war to actually calculate molecular structures by hand, okay? And actually, the methods that I employ are actually the great-grandchildren of these methods, okay? So methods that actually take a molecular structure and then use quantum mechanics to calculate its properties. So that's one of the methods that we use. And the other one, of course, is machine learning. I'm at Google, so I want to show a quote of Bill Gates, okay? But it's actually relevant, I think, the quote to Bill Gates. You can read it there and see why. Because, a breakthrough in machine learning will be worth 10 Microsofts, and, well, we're sitting here at Google. So now, what is the idea of screening, okay? So we have a space. Let's just be conservative. Let's assume the space of synthetically available molecules is 10 to the 60. I don't have the amount of computer power that you guys have. I'll show you have a lot, but I don't have as much as you guys have. And of course, I don't want to wait forever. So a reasonable size of chemical space that I can chunk is 10 orders of magnitude smaller than the number of available molecules. That means for a particular project, I can take about 1 million molecules, maybe it's 100,000, maybe 10 million. That's roughly the amount of molecules that I can actually look at in chemical space. So that first space of searching, reducing 10 to the 6 to 10 to the 6 is an art unto itself. There's a lot of stuff that we're developing in my group to do that. So I'll tell you more about it, but that's the first step. And then you're going to come up with different computational screens, hopefully a very cheap method first that actually can look at all of them and actually classify them and say, these are good to look at. These other ones, you throw them away, you use a better method, And then you eventually get to the point of the proof, right? You actually want to talk to an experimentalist to make the molecule. You want to go and convince some human to spend about half a year of their life in a hood with globes to make the molecule that you design in the computer. That's a very tough problem, and actually we work a lot in the theory experimental interaction software tools, actually, even how to talk to these people and convince them that it's a good idea to make your molecule. Actually, it's a very complicated situation. And then you want to feed back these very, 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 very rare data points that you're going to get from experiment and chop or modify your initial library as soon as possible and iterate as soon as possible, right? So in my group, we have done several projects that use this type of technology that we've been developing. I'll give you this talk in kind of an order of how we learned how to do things better. I'll start telling you about this Harvard Clean Energy project, which was our Generation 1.0 project. Then I move on to our organic flow battery project, which I like to call the 2.0 project. And then organic LEDs 3.0. And then origins of life is just cool, and I'm not going to have time to tell you about. But if anybody wants to talk to me about how life started, we're using these same tools to explore chemical networks and think about how life started, okay? But let's just begin by the beginning. So the first thing is, what type of molecules do we search for? When I say materials, I really talk about organic materials. More precisely, I like to think about it as the field of fine chemicals, just small to medium molecules or polymers. But what we do is actually very well aligned with the US Materials Genome Initiative. Actually, when this initiative was started, I got an email that I thought it was spam. It said, "Greetings from the White House." And I opened it, and it actually was greetings from the White House. They were talking to me about possibility of initiating this type of initiative. We were one of the few researchers that were doing that at the time. Now it's a big thing. The idea is, of course, we have, in the United States, we have this advantage of computational science, but done by people like you guys, big data. How can we combine those two with experimental tools to actually advance humanity in all these different areas and, of course, benefit the country and benefit the world? So we recently wrote a review in Annual Reviews of Materials Research that actually talks about the slight differences between screening for pharma. Every time I tell people about this, they say, "Oh, why don't you work on pharma?" Well, I tell them it's kind of quite hard to predict if a molecule is going to cross the blood-brain barrier or if it's going to be, toxic to the liver and stuff. I prefer just to make sure if something sticks to something else or if it's bright or blue or something like that. Okay? There's less problems in screening for materials than screening for health. Okay? And finally, there's a lot of people that think about materials. They just think about solid-state materials. Turns out there's very few alloys, very few periodic materials. There's many more ways of making molecular Lego pieces than periodic materials. Okay? So anyway, that's just a different type of features of this space. I'm not going to go into detail. Now, I have a new metric, which is, the metric is like, if you want to measure the success of a theoretical chemist, you want to figure out how many materials this person has predicted, and they have been made, and have been characterized, and they are actually good materials. And if you apply this metric to most of my colleagues, including me all the way up to 2011, the measure will be 0. That's the expectation value. Okay? Many people talk to you about it. Say, oh, I'm going to make materials in the computer and so on. And it is because they don't talk to the experimentalists. They don't do a lot of screening and so on, that they are not successful. And we've been painfully trying to be more and more successful about it. So when you talk to somebody that does this materials genomics, as this field is called, ask them, how many materials have you predicted? That's the first thing you want to talk to them about. Okay? So this is our first one. Look, this was actually cutting down chemical space of 10 to the 60 to 8. Okay? So we had this very, pointed idea that variants of a particular molecular crystal were going to be good. So we calculated 8, predicted the molecular crystal structure, which looked like this. And then finally, our collaborator, Jean Bao at Stanford, called us with the news after several years. We started the project in 2007. Okay? So 4 years. We convinced people to make it, and it was measured, and the postdocs were leaving and coming. We end up with a molecule that has a whole mobility of 13 centimeters squared over volt second. The figure of merit, for example, is a morphosilicon is about 1. There are much more conducting things like pure silicon, right? In hundreds or thousands, but this is actually really pretty good. Okay, so it's at the time it was the second highest whole mobility material, organic material, which is good for flexible organic electronics and so on. So that was our first one. So at least we have one, but we screened 1 molecule, sorry, 8 molecules. The first idea in my group, and we started in 2006, was, well, let's try to go and try to come up with these materials. This is the first world view of the materials I'm going to tell you about. They're called organic photovoltaics. You can imagine printing out these flexible plastic devices that you can put as curtains. So I could replace the curtains in this beautiful Sony building with actually light harvesting units. Or I can cover your parking lot, or I can cover the huge freeways of Los Angeles. Or super importantly, I can charge an Android phone by using a pad, right? That would be very, very useful to me, at least. But now, that's the first world view, and actually the company that did this, Konarka, is Under. Okay? The real use, I think, is more for this type of people. Okay? You have 1.4 billion people in the world that have no electricity. You want to get them off the grid. You have these people that could potentially use these little panels here to harvest sunlight for the house. You could imagine having the reverse organic light emitting diodes, flexible ones, so she can read at night. And actually, this is actually work of Sheila Kennedy out of MIT that is thinking of these flexible photovoltaics. She's working with Huichol Indians in Mexico. And think about that. They can even make solar ponchos, as you can see here. Right? So that's uber cool, right? What would be more hipster than having a solar poncho? Okay? So that's the kind of thing that I think really can change humanity. Okay? So now, see if my clicker works. Oh, there you go. That dude is calling his mom there. Okay? Okay, so that's the idea. So how does organic solar cells work? A little bit of chemistry. You have this blend of donor material and acceptor material, a material that absorbs sunlight majoritarily, creates what is called an exciton. It's an electron and hole pair. Okay? So in inorganic materials, they separate, and that's how most photovoltaics work. But in organic materials, the electron and the hole are bound to each other, so they move around together until they reach an acceptor that dissociates, sucks the electron, and leaves a hole in the donor. So I'm going to show you an animation that one of my undergraduates made about this. But first, before the animation, let me just tell you a little bit about chemistry. There's molecules are quantum mechanical. They have energy levels that are discretized. So one of the energy levels that matters is the highest occupied molecular orbital, or HOMO. Right? Is the last energy level, the quantum mechanical, that is occupied by 2 electrons. And then the lowest unoccupied molecular orbital, okay, is the one that you can excite into when you form an exciton. Okay? So the relevant parameters for this very simple model is that the gap, or the energy difference between the HOMO and the LUMO, and the position of the HOMO or the position of the LUMO determine the relative position with respect to the acceptor. You want the acceptor to be lower in energy. And you also want the HOMO as deep as possible, ideally, of course, below oxygen. Otherwise, your plastic solar cell oxidizes. right? Which it will suck, right? If you make this plastic that harvests sunlight and then it oxidizes. So those are the design parameters that we are after in this particular project. And this is a video of my student that shows you the mess. This is actually an atomistic morphology obtained from Jenny Nelson in Imperial College in London. We just made a beautiful animation around it of the electron and hole moving. This is not the results of any simulation, but it gives you an idea of the messy structure of donor blended with acceptor. We have a dramatic rotation around the acceptor, and then now you will see the electron go to the fuller ring, which is in the acceptor in this case, and the hole will remain in the polymer. Now you have this beautiful journey across this amorphous material all the way down to the electrodes, closing the circuit, and then basically generating a current that hopefully you can store in a battery or connect to your iPhone. So anyway, so that's the story. This is an amorphous material, and the question is, well, do I need to simulate all that amorphous stuff, or maybe I can use techniques like machine learning and related tools to actually learn something about it? So now this is the model, the very simplified model that we use to begin the screening. Markus Schaber, actually formerly at Konarka and now a professor in Austria, developed a model that says that if you have a band gap of about 1.5 electron volts and a LUMO level of -4 electron volts, then you have about the 10% efficiency of the polymer, or the molecule. And if not, then you're about 2, 3, 4, 5% solar conversion efficiency. That means the efficiency that you get of thinking about the power conversion efficiency of the sunlight coming in to power that you can draw out of the solar cell. Okay? So based on that, what we did is, well, let's try to slice up chemical space. So this is the first decision that could have been done better in generation 1.0 in our project. We talked to our experimental colleagues at Stanford, and Shannon Bao told us, well, these are these 26 fragments that if you combine combinatorially, you can come up, maybe there's going to be good solar cells there. So we said, okay, cool. So we wrote a script. You can imagine, Python combines all the molecules. You end up with 3 million molecules. And there you go. How do we compute them? So then that's when we started to harness some of the computer power out there. Some of you might remember, if you're old enough, the SETI at Home project. It's still going on, but when I was an undergraduate back in Mexico, this was really cool. People were just downloading the screensaver to Fourier transform the sky and find these little green aliens here, right? So that's basically what they did at the time, and what I did is basically partner with IBM and with Stanford, and now we're partnering with Buffalo, my former postdoc that started this project, and we started the Harvard Clean Energy Project, which actually uses the IBM World Community Grid to use spare CPU cycles to compute. Of course, what we do is generate also a beautiful screensaver and calculate. We have calculated roughly 30,000 CPU years. That's equivalent to about 500 million quantum chemistry calculations. So this is, to our knowledge, the largest ever quantum chemistry survey. Okay. So again, this is another video. Of course, at Google is going to be very primitive, but you can imagine what we're saying here. You're going to have these 3 million molecules. You're going to distribute over all these banana computers that people have around the world. And then in each one of those banana computers, you're going to actually compute one of these particular oligomers that we generated combinatorially, and then try to find which one is the golden one, right? So that's basically what we did, and maybe, if you are lucky, you get the lottery, right? So how efficient is this process, right? Let's see. So that's basically the Schaber plot. Remember, this is the region here that you have about 10%. This is the first plot probably you have ever seen that has log of number of molecules calculated with quantum chemistry. Usually each molecule takes 12 hours of computer time. This is an aggregated, huge data set, right? That shows you that the 10% efficient solar cells is about only 1.5% of our sample, or 35,000 molecules, right? So I love my donors of computer time, and I'm working towards making them more useful, because right now I had to apologize to them in the sense that most of them were computing very crappy molecules, right? So only 1.5% of them were doing good molecules. So can we do better than that? And of course, all of you Google people say, yes, come on, do things like Gaussian processes, right? So can I fit a model, right, that allows me to sift through these molecules before I send them for quantum chemistry to all these poor people that are donating computer time? Let me build a little model that actually is calibrated against the experiment and can help me quickly sift through this. In other words, add another layer okay, and of course, a Gaussian process is an n-variate Gaussian distribution over your n observations. It's a very beautiful theory, okay? And you guys know much more about it than I do, I guess. But of course, you have to come up with some function that is called the kernel that gives you some idea of the distance between these two different objects. So you have to encode them in some sort of function x that we'll discuss in a second. You have to have a length scale and this prefactor here that gives you an idea of your own choice of what's going to be the distance. So the hyperparameters you're going to pick, there's going to be the distance between your points. So there's a maximum covariance and the length of this kernel. And what do you put in? And actually, I was talking to Hartmut a lot yesterday in dinner. What exactly do you put in there to identify a molecule? So now we borrow from our pharma colleagues. And our pharma colleagues say, well, we have this algorithm called Morgan singular fingerprints that takes the two-dimensional structure of a molecule, looks at it as a graph, for example, this carbon atom, and starts going recursively in the graph and looking at all the nearest neighbors. Okay, and that's the concept of a chemical functional group, and generates a binary string. We usually use 512 or 1024 bits. You can generate them of arbitrary length and depth, and there's a lot of redundancy checking, and there's a lot of stuff that goes into this algorithm that I don't know all the details of. But you can use it as a black box and say, here is a molecule. You have a few parameters that specify how to generate a bit string out of it. It's like a hash of the molecule. And then you can come up with binary similarity measures. And I love to find these papers that are kind of encyclopedic. There was a paper that was doing clustering of all the different binary similarity functions and historical analysis of them. There's tons of them. The simplest one, actually, Jacquard, actually comes like this. If item 1 and item 1, if very many items present, this is the numerator. Over this, the denominator of present plus absent. Okay? And it was used in biology, actually. And it's one of the measures that you use to, for example, try to differentiate genomic trees. So you can think about different measures like Jacquard, Rogers, Forbes, Russell-Rao, and there's about 50. And you can see here a correlation of Tanimoto versus Forbes, Tanimoto versus Russell-Rao versus Rogers, etc. These are not very well correlated. But this is the type of choice that you have to make, and we just use the simplest one. Okay? So that's kind of the first thing. You set up a bit string that defines the molecule. You compare, and you use, of course, what is called a Gaussian process. If I have experimental data, this is important in chemistry, right? If I have experimental data with some experimental error bar, it will be these points here. Okay, now we know what the X means. It's this multidimensional parameter space of how close the molecules, the vector that will define, where a molecule is in this multidimensional space. And the Gaussian process, because it's this Gaussian distribution over all these points, has a inherent knowledge of what is good places, for example, to explore, where there's a lot of variance, or good places to exploit, perhaps because this is a place where I'm going to find a lower function of a lower value of the function. So this explore versus exploit is, of course, very natural here. So now let me just show you a simple force graph diagram. Okay, basically, how is it called? It's called directed force diagram. Okay, basically, it's a kind of like a visual way of clustering. I'm going to show you an experimental database that I did with my undergraduates of about 500 different experimental data points. And don't worry too much about these parameters. I told you about HOMO, LUMO. This is the percentage power conversion efficiency of the solar cell, open circuit voltage, short circuit current, etc. And you can see the point here is that you see clusters of about the same color. Right? That's the only thing I want you to see here. This is not a chemistry lecture, right? But that tells you that I can mount a Gaussian process on this thing because when I actually cluster my molecules with this HL is proportional to the Tanimoto distance, at least with the eye, I recognize some patterns. So that's kind of like a hand-waving way of telling you that Gaussian processes work here. I can show you data offline and a lot of stuff. But what we learn from this process, for example, even from the first 1.5% top candidates, we can learn, for example, which molecules are statistically enriched, which fragments. So if you want to make solar cells, instead of making them at random, I'll recommend you to actually use fragment 26, 24, 17, and 15. They're statistically better than all these other fragments. And my organic chemistry colleagues, honestly, what they're doing is they're trying to use their chemical intuition, but they are randomly sampling this space. So therefore, most of the solar cells that are out there are 4% efficiency, which are about the same maximum of my distribution, roughly. Right? So this can allow you to do this. But now, I told you I don't want my volunteer donors of computer time to see this talk and stop computing. I want them to continue computing. So now, because we add machine learning, we can actually prioritize and then calculate with quantum chemistry. So this is a neural network model of the actual power conversion efficiency versus our predicted one. You can see we have problems around 0. They have to do with the neural network, blah, blah, blah. This is an old plot, so we have now we have much better correlations, cross-validated, etc. But of course, what you want to do is just take the best ones from the neural network of these huge spaces of molecules. Now you can go to billions if you want, right? And then now go and compute the millions that you can compute, right? So that allows you to go several orders of magnitude beyond what you could do before. So that's why I want to talk about this here at the machine learning company. Okay, so I don't have to tell you what is a neural network, but this is what I'm going to do in my sabbatical, become an expert in this. Right now I'm the level of maybe perhaps a first-year graduate student. But of course, the idea here is that you have a bunch of bio-inspired nodes here that are basically summed up and activated non-linearly to come up with this network that has inputs and outputs. And in this case, I'm just giving you one of the simple neural networks that doesn't have feedback mechanisms. Okay, and the things that we use, and I tried to show you some of the techniques that we use, are probably very primitive for you, but whatever. We use RMS-prop, okay, which basically we do mini-batch layering with RMS-prop. This is kind of standard stuff. We parallelize it with Microsoft's Hog-White algorithm, which is pretty good for us. And something very important for us is that we learn all the things at once, most of the properties at once, and we find out that our neural networks are actually much more robust. And now I'm going to show you a result of our better neural network that it was already submitted, sorry, this is already submitted, but shows you that we can throw away most of the molecules in this area and just compute these ones. So you notice there was a lot of waste in this computation and projects, and so we started thinking about other ways of improving on it. Nevertheless, if you actually want to go and look at all our results, they were generated by the public for the public. This is a hippie project. You can go in there. Our database is being rewritten, and you can just go in there and get all our molecules. We're even writing a little game where you can draw molecules and get their efficiency, stuff like that. But now I want to spend more time telling you about the next generation projects. So first I told you about generation of electricity, but in a renewable world, we face more issues. This is actually, I was in the Galapagos Islands, poor me scientist at the conference, and one of the islands, San Cristobal, is powered 50% by these 3 windmills. Just think about that. You go there and look at these 3 windmills, and 50% of the island is getting its power from these little windmills, and one of them is even lazy there, right? That is just amazing, right? What's the problem with windmills, right? Those guys have a diesel generator to complement the windmill because, of course, this is a problem. This is the wind supply. This is the solar supply. As far as I know, there's no solar supply at night. But in the demand, it goes up and down and up and down and up and down and up and down. One time I saw the grid demand of Brazil during the final of the World Cup, okay? And it went down to 50% usage almost, or something crazy like that. And you can even see the middle of the game, like the 15 years of research. How do you call it? The intermedio. You just see the electricity go up because people open the refrigerators. Okay, you can actually see that. So it's very predictable sometimes. So it has these fluctuations. You have to compensate. And these things that we drew here artistically are batteries, right? So one of the very important components, and California just demanded batteries to be installed in the energy grid, are there to regulate the grid if you have a certain critical threshold of renewable energy, right? So that's the idea that can also help us go to those 1.4 billion people and tell them, what is the electricity N-star here? Which one is the electricity utility here in LA? California Edison. Screw California Edison, right? Get off the grid, right? Connect to this thing and just do it your own, right? So that's what you could do if you were in the underdeveloped world, in the developing world. If you don't have access to the grid, you might as well just not connect to it. Or if you want to feel very good with the world, you can do this as well, right? So that's what we're interested in. This is a company based in California called Enervolt that has this test system. Just to show you how they look, you have these solar panels and you have these big batteries. But this is not like the batteries you have in your cell phone. They're slightly different, and they're called flow batteries. What do you mean by flow battery? Energy is the amount of chemicals you have. And power is the amount of electrochemical cells you can use to actually convert that energy into power, right? So therefore, you want to decouple them and use pumps, right? You want to have a system that you can regulate the power, regulate the energy as much as you want, okay? So flow batteries are what you want to use for large-scale energy storage. So there are these tanks with pozolite and negolite, two different solutions that during the day you charge, say with your solar cell, and during the night you withdraw. Or you can use them to arbitrage electricity prices. That's very important. You can get rich by buying very cheap electricity and then selling it when it's very expensive. And of course, you can make a lot of money doing that. And this is what our president has to say about this.
And it's a company that provides multi-megawatt energy storage solutions using, and I have no idea what this is, vanadium redox fuel cells. That's one of the coolest things I've ever said out loud.
So I'm his fan, and this is awesome, but there's a problem with this, okay? And again, I love Obama, but there's a problem. There's not enough vanadium in the world to actually store the energy that we need, even if we top all the vanadium, okay? So me, I'm Mr. Organic Materials guy. We started working on organic materials. Can you replace this with an organic material, right? So therefore, ARPA-E, which is our funder, ARPA-E is like the DARPA of materials, and we were one of the few projects that have ever been renewed at ARPA-E, made a promotional video. And of course, most of it is experiment, and this is what they devoted to us as theoreticians.
Our energy storage efforts has led...
That's our Camille, okay? But what we did is we actually screened and found this molecule I'll tell you about, which is better than vanadium. And how do you screen first? 10 to the 60. What do? Open a chemistry textbook, okay? And you look at the different classes of molecules and look at which ones are between 0 and 1 is more or less where you want to be, okay? And then you say, well, maybe I'm not going to use amines and I'm not going to use olefins, but perhaps quinones are good, right? So that's it. So we said, let's go to quinones. Okay, so let's make, probably you guys don't know too much about quinones. Quinones are in all plants. They're electron transfer agents in plants, shuttle electrons back and forth. They're using photosynthesis. We also have them in our bodies. They're also laxative. If you have, if you have problems in your stomach, you can take a ray, and you can also use it to make cakes. And if you really want to attract female cockroaches, you can also put it on top of yourself. So it's a very important chemical messenger. It's dyes, there's stones of quinones, like alizarin, that are dyes in your jeans and stuff like that. They're used industrially by the tons. And at Harvard, where I come from, actually, even in the 20s, Louis Fisser, which is a very famous professor in my department, was already saying they are very different than all those other molecular classes that you were talking about. Why does he say they are different? Again, this is not a chemistry lecture, but the whole point is that they are swimming in the water, and they can take 2 electrons and 2 protons at the same time. Unlike vanadium that can only take 1, these little suckers can take 2 at once. Okay? That's very useful because then you can double the energy density, right? And they are reversible, and all the parameters that we know, pretty much physical-chemical parameters, are better than vanadium. Okay? So we already beat vanadium in our first paper. Okay? So how do I calibrate? Let me show you this 1964 machine learning. Okay? We actually just calculate the energy of the molecules correlated with the free energy, and we calculate this with respect to experiment. This is an experimentally measured reduction oxidation potential, and this is something that comes out of your quantum chemistry. 1969 was already known in chemistry. You can do this. So now I'm showing you machine learning of 1969. So we do it better, and now we can correlate very cheap quantum chemistry calculations with the observed values with R-squares of 0.97. Okay? So that allowed us to build, first of all, we learned a lesson. We were not going to build a library of 3 million molecules, neither of 8. We built a library of about 3,000, and we went to screen. Okay? And in about 3 months, our library looks like this. These are the benzoquinones with R groups. There's 17 different groups that we plug in here. Now you can see the Lego nature of this. These are benzoquinones, naphthoquinones, and anthraquinones. So all these little places where you see a little R here goes with 17 different substitutions. Okay? And again, you can do it in a script in an afternoon. And then you have a distribution of the redox potentials of these quinones. The textbook was wrong. There's a much more big variety of quinones. And you can actually catalog them by the type of quinone. Here are the redox pairs of vanadium that Obama was talking about. And you can replace vanadium and test it in the lab. Meet with experimentalists every week, and that's painful for a theoretician to be listening about experimental details. But that's what Google Chat is for, okay? And then we found this molecule, anthraquinone disulfonate. We like to call it Jesus Christ quinone, okay? And it's very cheap. You can actually, 2 synthetic steps or so at the industrial scale can give you Jesus Christ quinone, okay? And maybe it's the savior, okay, for the world, okay? And here it is. Our paper is in Nature. It has our little Harvard scale flow battery. Of course, we're working to scale it. And as I told you before, the most important thing is to have engineers, experimentalists, and theoreticians working together. Most of the theoreticians that work on this work by their own. So then nobody wants to make their stuff. You have to talk to them every day, work together. They have to tell you what to do, and you have to tell them what to do. You work together. Okay? So you need always experimentalists. And Shang Won-Soo in my group, which is very good at visualization, summarized all our hundreds of thousands of calculations in this type of correlation plots of different types of quinones and what they do, for example, to the redox potential and so on. Okay? So that's the kinds of things that you want to do because an organic chemist understands this visually. So that's the extra mile you have to go. For example, OH lowers the redox potential, but there are some families of quinones that have a slightly different tendencies than others. And anyway, so we were able to do the low potential of the battery very well. We're still working on the high potential of the battery, so we need another molecule for the high potential that is not anthraquinone disulfonate. And we're doing screening towards it, okay? Now, this is where our software tools start to come up. We have, of course, databases that we can actually go in and search. And you can see the stable molecules are in blue and the unstable are in red. The potential goes from left to right, and you can see how this island of red molecules, the stones of red molecules there, that is a very good negative result. You can tell experimentalists, stop making quinones for high potential. And that's where machine learning and quantum chemistry can allow you to actually tell people, stop doing something and accelerate materials discovery by a factor of 5 or 10. Okay? Because you can just visually see the data, right? And we have data plots like this is 100,000, we have done 500,000 and so on. You see there's very few stable blue molecules there, right? So maybe you move on to a different family of molecules. After all, there's 10 to the 60 of them, okay? And of course, to you guys it's trivial, but we spend a lot of time with a software engineer, Tim Hirsel in my group, filtering the data. But here is basically a baseball card view. Okay, so we discovered that to talk to experimentalists, the best idea was to think about baseball cards. We say, look, here are our top molecules for this weekly batch. So we have this system where we have batches, and we discuss the batches with our collaborators. You look at the properties of a particular batch, and now our software system is more advanced than these videos. You can actually click on the molecule and see it in 3D and do all sorts of cool things. And underlying it, we have a lot of data structures. For example, if you want to look at a molecule, how it reduces or oxidizes, you have to consider all the possible reduction oxidizing pathways and come up with the lowest energy one. And this gives you an idea of what is the plumbing that is behind our databases. Okay? I thought it was cool to show it here. So now in the last 20 minutes, let me tell you about our latest story, Generation 3.0. We were approached by Samsung because there is an issue with organic light emitting diodes. Some of you might have Samsung phones here. And I have to tell you that any phone that has an AMOLED, the blue pixels die sooner than the manufacturers want. Okay? So if you were able to solve that problem, then there's going to be AMOLED displays everywhere. Everywhere. Okay? You could replace these LCDs and stuff like that. So we started working with them. The market is huge. You can also think about LED lighting. You can think about beautiful, flexible applications of LED. The market is huge. And of course, you can think of flexible displays. And the other different type of cell phones, like the Amazon Fire, iPhone 6, or LG, are actually LEDs instead of organic LEDs. So how does organic LEDs work? They are the opposite of the solar cell I showed you. I don't have a beautiful animation. But you generate carriers in the electrodes, exactly more or less the same morphology of the solar cell. But now you run it in reverse. You put about maybe 5, 6 volts. The charges localize, and they emit light. Okay? So now let's learn a little bit of chemistry. Okay? What's the problem? The problem is that molecules have something called triplet, an excited state called triplet that has 3 excited states that is not bright. It doesn't emit light. And it has a singlet that is bright. Electrons and holes come in a statistical distribution, and therefore you have 75% chance of landing in this triplet, okay, that phosphoresces. Phosphorescence is bad. Basically, phosphorescence means delayed emission. It stays there forever, and because quantum mechanically cannot emit light, it just stays there and emits the light very slowly. That sucks for a display, right? You want as much as possible emission from the singlet, but you only have one singlet. So you basically lose 75% of efficiency right there. Well, how about these phosphorescent materials like phosphorus that you can see they emit light very efficiently from the triplets? How does that work, right? Well, usually you have transition metals that increase a quantum mechanical effect called spin-orbit coupling. Okay? So the rate of emission goes as the spin-orbit coupling over the gap between the singlet and triplet. If the singlet and triplet are close in energy, you can overcome this effect of the spin-orbit coupling. Okay? Well, the state-of-the-art materials that are in your cell phone actually use transition metals to enhance this spin-orbit coupling. And this curve, the only point of this curve is that they have saturated to about 1 millisecond emission decay time. Sorry, 1 microsecond emission decay time. We have not been able to move on beyond this, and this is the state-of-the-art of OLEDs. What is the problem of the blue? You have this metal molecule bond, okay, that has cycling of several, a few volts every time it emits. So what happens to the bond? It breaks. So can I replace that metal by something that has no metal? So I'm no metal man. So let's replace it by a molecule that has no metals. Okay? And for that reason, because these molecules break, if you go to Amazon, you find displays for $9,000 and lamps for $4,000. Okay? So with my professor's salary, I cannot afford those. But Chihaya Adachi in Kyushu University made a breakthrough. If you actually have molecules that have a very small singlet-triplet gap, you can have thermal excitation from this level can take you to this level, and you can fluoresce from this level. In other words, the triplet, there are 3 levels here, can activate, so that's why it's called thermally activated delayed fluorescence. It will activate back here and fluoresce back, if you know what I'm saying. The problem is that most of these molecules are not bright, okay? And because they are not bright, people thought this was not possible. But he found molecules that were exactly like Goldilocks, bright enough, stable enough, and had this effect, okay? And it started a revolution about 5 years ago. And that's when Samsung approaches and says, can you help us with your computers, help us overcome all the amount of development that these colleagues have. So I got together with my collaborator, Ryan Adams. This is a very good moment to mention him. All the machine learning I've been doing has been inspired, informed, collaborating with Ryan Adams. He's awesome. Our synthetic collaborators at MIT, Tim Swagger, Stephen Buchwald, the most cited chemists in the world, Mark Baldo, Troy Van Buris. So this is a team. We have done more than 150,000, but maybe 250,000 or so molecules screened so far since we started this project about a year ago. And we have sent several tens to synthesis. This is also outdated. So how did we win here? How can we be successful? We came up with very good OLEDs. I'll show you at the end. Well, because now we spent tons of time thinking about the cutting of chemical space. And the story goes like this. In the first program review, I showed the molecules to my collaborators in Korea, and they were saying, I hate that molecule because of this. I hate that molecule because of that. That molecule will never work. That molecule will never work. So we implemented a lot of tools to blacklist, symmetrically roll the molecules, press screen fragments, et cetera, et cetera, et cetera. So all our effort came into very good ways of generating the first screen of 10 to the 60 to 10 to the 6, so that everything that our colleagues saw at Samsung was pleasant to them. Okay? And I think that's the key to materials design. So this is our first generation that when they saw these molecules, they were scolding us. That's ugly, right? But the second generation, now we're already in the third one. So I got a Blast Charlie. So Charlie is very pleasant. But Blast, 190,000 molecules, was symmetrically pleasant. This looks like a spaceship type of molecule, easy to make. If you're an organic chemist, you will like it. But you don't like to make this one. Okay? So how do we do that? Well, we increase the number of possible fragments to actually have better IP space. So this is the number of fragments that our Japanese colleagues have used, TADF Adachi. Other groups have come up with these ones, and we come up ourselves by screening the fragments. All these new fragments are going to our libraries. And of course, the ones that come out of blue against blue are good in the IP sense, right? So this is just a plot to brag about the fact that every time we improve our libraries, they become better, more symmetric, more fragments, more blacklisting rules, which basically means more filtering before we even compute something. And therefore, we have more entries per fragment. Okay? So I'm running out of time, so I'm going to skip this slide. I want to skip this slide too. But we do exactly the same thing that we did in the clean energy project since the beginning. We sample, a few tens of thousands of molecules, we calculate them with quantum chemistry, and then we train a machine learning system, in this case a neural network, and that neural network allows us to prioritize the molecules and say, these are the good ones, these are the bad ones, and we only compute the good ones. And usually once we are done with the good ones, then we change to the next library and the next library. It accelerates discovery really quickly, okay? So again, we have to make a software system that uses all these tools, automate the scoring of how difficult it is to make a molecule, incorporate the chemical expertise of your partners, in this case Samsung, the fragments to be able to come up with a set of good molecules. For example, of these 588 combinations of molecules of this donor, bridge, and acceptor, symmetric molecules like this, notice the donor, the bridge, and the acceptor here, this Lego combination, there's only 9 out of these 588 here, okay? Now, you can actually start, we started using voting, I'll show you in a second, to actually rank the molecules, and you can see that there is this pharma descriptor called synthetic accessibility score that is roughly correlated with molecular size, okay? That basically anti-correlates. So if you have a low assay score, organic chemists find the molecule pleasant, okay? So now you can also screen over synthetic accessibility score, which is a pharma type metric for how easy it is to make a molecule. And now let me show you. This is our first device done about maybe 8 months ago. I don't remember exactly. This is a video of our first device.
Can you do it again?
And I'm laughing there because it's a blue.
Yeah, there's some dying parts.
And just today, I got an email from Harvard. We have for you it won't mean anything, but we have a 16.7% external quantum efficiency device. So if our colleagues from Japan are looking at, they know we are exactly at the same as them, right? So today, we caught up to them in 5 years, in a year, okay? And this is the email I got this morning, literally at 8 a.m. here, because of course, Boston is 3 years ahead, okay? So I got this 16.7% email, right? Because we just got the news from Korea that, of course, was working before. So Korea sent us overnight the 16.7, and then they sent it to me, and then I show it to you. So this is Tim Hirsel, Rafa Gomez Bombarelli, and Jorge Aguilera. Super happy with the 16.7. And of course, there's all these other group members, people from the Valdo, Swagger, Adams Group, Samsung, etc., that have been made possible this molecule that is as efficient as the best ones in the world right now in TADF. So now, what are the things that we do? Of course, we think about this type of companies like Tinder. My student Ryan Babush that is here introduced me to Tinder. He has the honor of showing it to me. And he's now going to be working at Google, actually. So Ryan showed me this application. I have never used it myself. But I was inspired by Ryan to actually do the same. And that's how I have my organic chemist vote on the molecules. And I learned from it. Right now, not machine learn, but just learn. I have very few data points. But I have people from MIT, from Samsung, from Harvard vote on these molecules and tell me if they like them or not. And this allows me to actually figure out. And here is the baseball card, much more complicated for an organic light emitting diode. Okay? So this is kind of our new network. This is generation number 3. We have people voting in the computer. We have high throughput screening that involves several layers that include quantum chemistry, semi-empirical methods, machine learning, blacklisting, a lot of library generation, and a lot of feedback, generating libraries every 2-3 months that are better and better. Okay? And that shows you a progress of about 10 years in my group that allows us to think about materials. This is actually the last data slide because I know I'm running out of time. This is actually from the group of Ryan Adams. This is Miguel Hernandez Lobato, another Spaniard. There's many Spaniards in this project. If you glue 2 neural networks together like this, you can actually come up with like the 2 principal nonlinear components. I don't know how to say this technically, but gives you the best 2 nonlinear dimensions to see your data set, right? And you can see these islands that are made by our library generation. So we generate in islands. And what you see in gray is crappy molecules. And when you see in red is good molecules. And what is encoded in this, if you actually go as a chemist and look at these islands, they are combinations of donor and acceptors. So there are rules, right? So this is to me to learn what the heck this neural network learned. Okay, I do this and I find out the good combinations of donors and acceptors. And now I can tell my experimentalist colleagues, do not please make any molecule in this island. Even if you think it's good, right? There's nothing there. So I call this like sailing the Pacific when you were like a Polynesian. Maybe they were sending many boats and they never came back. But when they found Hawaii, they all went to Hawaii. So that's what happens to us right now when we're making organic light emitting diode molecules. Our latest batches are full of golden molecules that Samsung can go and test. And this is kind of like what I wanted to be. And now, because I'm at Google, I'm showing you a plot of an Apple person. But I really like this quote, okay? That to design something, in this case molecules, you really have to get it, and you really have to be passionate, and you really have to be then 10 years at it, okay? So you have to take your time, and it takes a lot of effort, and I show you all the effort that it takes, and that's why I like this plot. This quote of Jobs, and I'm going to show you a time result picture of my research group, thanking them all. Ryan, who is going to be a new Google employee, is here with his cool glasses. Borja, by the way, is also here visiting. And finally, a small advertisement or a small development was that we're getting so good at it that we're actually spinning off a startup company called Calcularia, the place where you do calculations. We're going to actually do this, and we hope to be the first chemical company without labs, like the Uber of chemical discovery. So that's our company that's being spin off of my lab right now. And with that, I open up for questions. Yeah, and thank you for your time. Yeah. Let me put Jobs there, not to distract. No questions?
I know that there's a whole number of folks behind the camera on some related projects. I'm not sure, would they be able to ask questions? Or?
Yeah, this one question. Yeah.
Okay, so I have a question. The question is, in the chart that shows the 10% efficiency rate, is that the maximum we can get from solar cells?
That's a very good question. What is the maximum that we can get from solar cells? That's called the Shockley-Queisser limit, and it's computed about 30-something% for a single junction solar cell. You can go for multi-junction solar cells to higher limits. In the case of these organic solar cells, with a single junction, because of all the losses and so on, you can get about 15% maximum. But the 10% is more like the commerciality threshold. If you can make a solar cell that is about 10% efficiency, it's actually cost efficient to put it on a rooftop. If it's below that, then it's too low density. So it's not so, because most of the cost of a solar cell is a back panel and the module and so on. So even if you have a free plastic on top of it, if it takes too much area, it's going to be expensive. So it has to be at least 10% efficiency. We're working on solar cells with many junctions, so it will be not very soon that experimentalists and theoreticians will come up with solar cells that are 20% efficient or so. I think that's not far away in the future. That will involve just two more layers.
Thank you.
Alán, as a machine learning person, one of the first questions you would ask is, when you want to train a classifier, is how many input-output pairs you have. Now you had different projects here, but can you give us, for some of them, an order of magnitude? Let's say how many fingerprints for molecules you have, and then associated with, let's say, efficiency.
Sure. For example, the largest data set is the Harvard Clean Energy Project. If you want to learn the quantum chemistry results, you can have a molecule and compute this quantum chemistry. So first, let's talk about learning quantum chemistry. Okay? There you can run as many quantum chemistry calculations as you want. So in the Clean Energy Project, the neural network that we used was trained about 200,000 points. Okay? And it was a 3-layer neural network, typical deep neural network of 128, 64, 32 nodes, like that. And that was trained on about 200,000 points. Now, the Gaussian process I showed you that we put before, that's the process that calibrates experimental data to the quantum chemistry data. Okay, so we have two things. First, a Gaussian process that takes you from experiment to quantum chemistry. And then we have a quantum chemistry predictor based on a neural network. Okay, so there's two levels of machine learning. The first one was about 500 data points experimentally harvested. And that's what we use a Gaussian process there. Because it allows us to know the errors, and it's actually probably cleaner, in my opinion. Then for the Quinones, we used maybe about of the order of tens, maybe 20 or 30 experimental data points. In that particular case, this R-squared linear regression is perfect because it's a long story, but it has to do with the fact that these molecules almost have no entropy when they're reduced or oxidized. Therefore, it's basically just enthalpy, and you can use quantum chemistry, get very simple numbers, and correlate them with a complicated free energy. So there we use maybe 30 points. So you see, so if I want to learn quantum chemistry data, I can use as many as I want, and usually go to tens of thousands. For example, in the case of the OLEDs, okay, in the case of the OLEDs, OLEDs in some sense are easier than organic photovoltaics, and we can get away with between maybe 10,000 to 40,000 quantum chemistry calculations per batch to train a neural network to predict the entire batch. So if I have a batch of 500,000 molecules, right, I can machine learn it with about 40,000 entries. And then my neural network is good enough to predict the rest.
So I mean,
does that make sense?
No, so I think that was quite helpful. Let's say for large training jobs, let's say in image recognition or so, it wouldn't be unheard of to even use 10 to the 9, 10 to the 8 training samples, or much larger numbers than you were just quoting.
Yeah.
To generate such huge data sets or let's say, where do you perceive this as a bottleneck? Is it more on the computational infrastructure, that if you, let's say, it wouldn't be a problem for you to generate 10 to the 8, 10 to the 9 samples, but then learning from it is difficult, or in many cases just inconceivable to get useful input-output pairs of that order of magnitude?
Well, I think for me the bottleneck is two things. The bottleneck is human, what to screen for, and to get the data out of the literature to make the models. I think the computing is about 25,000 molecules in a small cluster per week. You can go even beyond that. You can use the cloud and do as many as you want. And then the learning has never been a bottleneck. We had to parallelize our learning with Hogwild and things like that, but you could use a lot of tools, maybe Google's tool, to learn this. I would say the bottleneck, I think, is to make the right decisions about what's going to be your library and how to chop it. So any automations, what are the observables there? So any automations like data scraping would be awesome for me. If I can data scrape all the data tables and materials, for example. And also if I have tools for building my libraries more automated, which is part of what's going into Calculario, all the developments that we did into how to make libraries. So I think there is a bottleneck, not necessarily the computing or the learning. It's just the initial part of seeding chemical space, needs humans still, and does that make sense? Yeah.
Hi. Once you found the other side of that flow battery, how much more efficient is it going to be comparing to the vanadium existing, or how much time is it going to take to actually, you expect it to deploy a large scale battery?
So my colleague Dan Nucera started a flow battery company that was purchased by Lockheed Martin, which is very interested in this space. So there's big corporations that are actually entering the space to manufacture the flow batteries. So the actual battery itself and all that, there's big companies making it. Now the chemicals that go into it, the vanadium, right, is very expensive, right? So we estimate that our cost of the electrolytes, it's about at least 3 times cheaper than vanadium, even perhaps more. So we're going to win in the cost of the chemical itself. It can charge up to tens of thousands of times. So we believe that the battery will be there with stable quinones for 20 to 30 years, right? So you just replace them later. They are so cheap, right? So we basically lower the cost of the electrolyte. So, for example, the Tesla battery that was just announced is made of lithium. We can replace the battery today with that thing if somebody scales it up, way cheaper. Okay? We have a calculation I cannot tell you right now, but way cheaper.
So the materials themselves are very common, and the production itself is relatively cheap?
It's a fraction of oil, yeah.
Got it.
So you could use oil. Instead of burning it, you use it to store energy.
Thank you, Alan, for an excellent talk.